share our thoughts about binary search. Uh, okay, so first of all, binary search algorithm is basically a searching algorithm capable of finding in a certain array or yeah. So first of all, the algorithm. This is the algorithm itself. So what the algorithm does is the process begins with finding the keyword at the middle of a list, and then it starts comparing the key value with the element in the middle of the list. If the value of the key is less than the element at the middle of the search, then the search process the key to the list up to the middle element, and if the value of the key is greater than middle element, then the key from the middle element to the end of the list. So I'm sorry if this doesn't make too much sense, but here's a visualization of how this algorithm works. This is a simple example of how it works in a 1D array. So let's say our element that the key value that we are searching for is 7. So first of all, it will begins at the middle of the list. Oh yeah, by the way, I'm sorry I didn't mention it, but for this algorithm to work, it is very important that we sort out the list first. So as you can see that it will first begin at the middle of the array, and if the desired element isn't the middle list, it will check if the desired element is less than or more than the key value in the middle. So in this case, it's less than, so it will slice up the rest of the array and starts looking at the left side of the list. Then it begins at the middle again, and then it checks again. Then it and once uh, then it checks that whether the desired element is uh, less than or more than. So in this case, the desired element is more than the key value 6. It will start at the right side, then left side, and then it find the desired element. Next. So here's the time complexity. My friend will explain much more.
So for the time complexity, uh, for the best case scenario, it will happen when the item X is in the middle of the array A. A constant number of comparisons are required. For the worst case scenario, uh, it happens when the item X does not exist in the array, though each recursion or iterations of binary search, the size of the admissible range is halved. The solving can be done ceiling log n times. Thus, ceiling log n comparisons are required. For the average case, uh, it will take the sum over all elements of the products of number of comparisons required to find each element and the probability of searching for that element. To simplify the analysis, assume that no item which is not in A will be searched for and that the probabilities of search for each element are uniform.
So over here we have the advantages and disadvantages of binary search, and the advantage are the binary search is an optimal searching algorithm, and it's best for finding a certain element on a sorted list, and it's one of the fastest algorithm. And third, it doesn't actually scan each line of each element of the list, so it performs way more faster than linear search. And the disadvantage of binary search is that the list needs to be sorted first, and it requires more stack space since it uses recursive approach. And next on. So here, one of my opinions. So I think that the binary search algorithm is very useful, especially if you want to find out an item from a list. And one of a daily application of this algorithm is to find a certain page from a book. So suppose we have like this example here. Suppose we want to find a page 10 from a 20-page book. So what we do first is we open the book randomly, and here we get page 15. So that means if you want to get page 10, but we get page 15, that means that page 10 is less than 15. So logically, the page 10 means that it is on the left side of the list. So then we repeat the process until we get to page 10.
So also, in my opinion, even though the list needed to be sorted first, binary search makes it up by with speed. By splitting the data in halves until it found the right value, binary search can cut the computational cost of searching better than the other algorithm.
Okay, so that was some of our thoughts, and for our conclusion, binary search algorithm is a quite efficient algorithm for finding a certain item in a sorted list, and one of the most common ways to use binary search is to find an item in an array, and then the key of binary search is the item must needs to be sorted first. Uh, thank you. That's all from us.
Okay, thank you very much for the presentation. I think this is also one of the good presentation, yeah, from you. The search algorithm is always the the cool things, yeah, because when we realize that it is, for example, to find out any object or any elements on the planet, for example, it will be the search first, so that will be solve the world, yeah. So how we can save the world by do some searching activities. Okay, so thank you very much for this one. This
I'm
is
sorry, sir.
yes.
Sorry, sir. By the way, two of my group members said they couldn't attend the class because they were going to hospital. So
Oh,
yeah, that's why only
okay.
three of us presented.
No problem. Okay, thank you very much for the
No
information.
problem.
Hopefully, your group is okay. Just common illness or something.
They didn't specify the details.
Okay. Okay. Yeah. Okay. Thank you.
Thank you,
Okay, we
sir.
go through to the next group by Tian Aji group, please.
All right, sir. Give me a second. Are you guys able to see the presentation?
Yes.
Yes, good. Okay.
All right. So for our presentation, we have decided to do pancake sorting algorithm. My name is Diana Jiwibisana Purnama, and my group consists of Rizky Haji Putro, Muhammad Aldian Banyu, Ismail Seto Adi, and Alvin Januar. So this is the agenda of the following things. We will have preface, summary, cognition, execution, and opinion. So the pancake sorting problem is a classic example and is introduced in many algorithm courses. It was proposed by an American mathematician, Professor Jacob E. Goodman, in the magazine American Mathematical Monthly in 1975. Professor Goodman described a waiter navigating a busy restaurant with a stack of ant pancakes. To avoid disaster, the waiter wants to sort the pancakes in order by size. The only available operation is to lift an upper portion of the stack and invert it. So But the problem is, how do we find the maximum number of flips needed? Our next slide would be discussed furthermore by Seto.
All right, thank you, Dean. So to better illustrate the pancake sorting algorithm, we're going to try to solve a sample problem in which there is a stack of pancakes where each pancake has a different size, and each size is represented by an alphabet letter where A is the smallest pancake and G is the largest. So the stack has a random order of C, E, B, A, G, F, G, and we will do several flips to make it in the correct order of A, B, C, D, E, F, G. So we firstly lift the largest pancake G along with all the pancakes above it and flip them to move G to the top of the stack. And then we lift the bottommost pancake and flip the entire stack, which will automatically move G to the bottom. And then because G is already in the right position, we can leave it alone. Next, please. All right, so the next largest pancake is F, and using the same strategy, we lift it along with all the pancakes above it, and we flip them to move F to the top. And then we lift and flip the entire stack above G, and by flipping the entire stack above G, F will be automatically placed right above G. Next, please. All right, so the same strategy is used to move E, then D, then C. Hang on. Could you move to the next? All right. So the same strategy is used to move E, then D, then C, then B, and lastly A, so that we will end up with a correct order of A, B, C, D, E, F, G. So in total, there are 8 flips. Next, please. All right, so what was described above is actually the greedy algorithm version. And in 1979, Bill Gates, who was still in an undergraduate student at Harvard, he showed that the required number of changes in a stack of n pancakes is actually less than 5n plus 5 over 3. And in 2008, Gates' achievement was actually surpassed by a team of researchers from the University of Texas who established that upper limit is always 18n over 11. And the pancake sorting algorithm is used in computer science where it can provide an effective routing algorithm among processors in parallel processor networks. And it is actually also used in DNA rearrangements. All right, so my colleague Audrey will continue with a summary.
Yeah, unfortunately, due to Aldi not being here physically, I need to cover him up. So thank you, Seto, for the explanation. I'm just going to go ahead to describe to you what is pancake sort. So you guys might be wondering, we already have lots of sort algorithms like quick sort, merge sort, heap sort, bubble sort. Why the hell do we need this? So I'm just going to tell you what pancake sort is. Then I'm going to tell you how the original founder actually got thoughts of it. So pancake sorting refers to the mathematical problem of sorting a mixed stack of multi-sized pancakes, in which you will need to order the pancakes in order of size by using a spatula, where it can be inserted at any point of the stack. When the spatula is inserted at a certain point of the stack, the spatula then flips all the pancakes on top of it, thus altering the stack.
Oops.
So, as some of my colleagues have explained before, the original problem for pancake sorting was actually posed by Jacob E. Goodman on the American Mathematical Monthly under the pseudonym Harriet Waiter, in which he asked the following question. The chef in our place is sloppy, and when he prepares a stack of pancakes, they come out at all different sizes. Therefore, when I deliver them to a customer on the way to the table, I rearrange them so that the smallest winds up on top and so on down to the largest on the bottom by grabbing several from the top and flipping them over, repeating this, frying the number I flip as many times as necessary. If there are n pancakes, what is the maximum number of flips that I will ever have to use to rearrange them? So this problem actually is sort of a problem that has been answered by multiple people over the times. Some of them including Bill Gates and Futurama co-creator David S. Cohen in their respective times, of course, because they both provide two different papers in different times. So let's just go to Bill Gates' answer to this. So before starting, I'm going to explain that we already know the lower and upper bounds of the pancake stack itself, which is like approximately n, but to what extent? So in order to know what extent, we need to know the terms for pancake sort first. So first and only thing here, we have adjacency defined as in the text, where gxy indicates that no other pancakes should be in between x and y. With that being settled, we can now go to the rules. So number one is each flip will only create at most one adjacency. For n bigger or equal to 4, there are stacks of n pancakes that have no adjacencies whatsoever. And for n bigger than equal or 6, the function of n is bigger than n plus 1. So you guys might be looking at this and be confused initially, especially with what I've wrote there, but there will be an example later. So continuing to the requirements for the sorted stack. A sorted pancake must have all n adjacencies. So I factored the big O notation for Bill Gates' definition of pancake sort is actually n, where in exact we got the lower bounds of fn to be 17 out of 16 of n to 5n plus 5 divided by 3. So if you guys are confused with the rules that I've written, we can just go to the next figure that I've put, where Bill Gates wrote a table for the pancake sort in which the f corresponds to the number of n itself. As we can see here, the equilibrium is at 5, and when n is 6 or bigger, then f is bigger than n itself. Exactly as what Bill Gates wrote in the paper. So moving on. We got the answer from Bill Gates. So now we're going to go for the answer from David X. Cohen. This is taken from his paper, of which you guys can check the DOI over on the bottom right. So this variation took attention of the real-life situation in which pancakes can be burned on one side. And normally, if you go to restaurants and order pancakes, that burnt side of the pancake faces the bottom. So with that being put in mind, David Cohen made an algorithm in which he preserved the burn side on the bottom with a slightly worse algorithm. I mean, we also get the big O notation n, but here's the thing. The lower bound for the algorithm itself is 3 out of 2 per n compared to Bill Gates' 17 out of 16 n. And for the bigger one, and for the upper bound, it's 23 out of 14 of n, plus some constants for n bigger than equal to 10. So how this works, I'm not going to explain, but who's going to be explaining is Risky.
Okay, thank you, Alvin. Now that we have covered in depth the cognition about our pancake sorting algorithm, I'll talk a little bit more about execution, which is the practical aspects. Um, if the video could play on the left side, we could see that the specific rule set of the pancake sorting algorithm is to sort the pancakes from the smallest to the top to the largest to the bottom from the starting stack that can be arranged in any order. If such a flip occurs, you flip the entire preceding stack of pancakes. The next step is to flip the pancake to the bottom of the stack. We must first flip it to the top, then flip it again to the bottom. To order each pancake, we will require one flip up to the top and one flip down to its final location. Um, if we were to translate this into pseudocode, it would be as so. For I equals n minus 1 to 1, where n is the length of the array, you do the following steps. First, you would find the index of the maximum element. Then you would flip the array to move the ith max element to the first position. And then finally, you would flip the array again to move the ith max element to the ith position. And yeah, I hope the video that was played was able to convey that visually. Moving on to the actual execution of the PyCode, as you can see, the source is from Geek for Geeks. The first thing we would do is to define the flipping function so that the algorithm can figure out where in the array position it needs to figure out. Afterwards, it would return the index of the maximum element in array, and then the main function that stores the given array will use the flip operations that we have specified. Furthermore, next, we would start from the complete array and reduce the current size by 1, and this makes sure that there are no repetitions after we have found the maximum element. After that, we would find the index of the maximum element in the array, and then move the maximum element to end of the current array if it's not already at the end. To move to the end, you move the maximum number to the start, and then you would move the maximum number to end by reversing the current array. Finally, a utility function is just used to print all of our results. And by the end of it, you should get a listed array sorted from smallest to highest values. And if we were to analyze the complexity of this, where n is the number of pancakes in stack, the time complexity would be O(n) squared, whereas the worst case complexity would be 2n minus 1. 2n minus 1 because it has to always go back to its first initial location, then go back to its final sorted location. This is the worst case scenario if you have a big number and then a small number, and that alternates throughout the array. And yeah, next please. Now we will let Dean talk about our philosophical opinions.
So, for the opinion, pancake sorting algorithm is essentially a sorting algorithm based on a priority. So sorting is in fact an algorithm that is heavily used in today's information and internet technology. To function effectively and efficiently, we need to be able to prioritize. But what if we, as humans, become the object of prioritization? Society's constant strive towards prioritization can therefore be seen as a form where the strong dictates and controls the collective of the weak. This ideology can often be reflected as a form of eugenics, something Nazi ideology taught it as superior. As history has proven, this line of thinking ultimately become humanity's hubris, and as such, we must proceed with caution to ensure that our technology does not reach this form of cognitive thinking. And next is the opinion of someone in a group. He said, I never could have thought that one could see the problem in real life and then without a second thought, see how the problem persists. Made a solution, put it in another field that is not correlated to the original problem whatsoever, and somehow made it fit. Even better, the solution that is proposed here is better than any other sorting method. Without bisecting the problem, the average time for any other algorithms to sort is O and multiplied by log n. This signifies that so much things are still waiting to be discovered as a solution to all the problems that exist in computer science. That would be all for us, I believe. Thank you for listening.
Okay, thank you, Tian. This is very good. And the last paragraph, who have this opinion? I'm very curious because the talk is very deep. I think, yeah. I think even you not realize, but you get the point of the philosophy. I think when you say about that something can be fit into the problem, but the way that we want to solve this problem is not always in the field. Yeah, so that's cool things. Thank you very much for this very inspired presentation today. Thank you, Dan. Okay, and team. Yeah. Okay, so we go to next. I think go to Haidar Azhar. Yeah, please.
Okay, so please wait for a minute because my friend is trying to prepare the presentation.
Yep, no problem.
Also, sir, the person of who said that opinion was Alvin.
Okay.
So can everyone see the presentation?
Yes, please.
Okay, thank you very much. So, Assalamualaikum warahmatullahi wabarakatuh. For today's lecture, me and my friends are going to present about merge sort. So the group consists of five person, which have Linus, Faiz, Hanan Fadil, Tegal Taufik, and me myself am Haidar Azhar. Please next. So for today's discussion, we will talk about the overview of merge sort and how the algorithm works, the philosophy behind the algorithm, cognition and the computation of the algorithm, and last but not least is our thoughts about the algorithm. So for the next part, my friend will explain about the overview of the algorithm.
So the basic overview in merge sort. Merge sort is an efficient, general purpose, and comparison-based sorting algorithm. And it adapts the divide and conquer algorithm that was invented by John von Neumann in 1945. Then the detailed description and analysis of bottom-up merge sort appeared in a report by Goldstein and von Neumann later in 1948. Merge sort is a divide and conquer algorithm where it divides the input array or list into two halves, comparing the numbers in each half, and then merge the two sorted halves back. It has the time complexity of O, big O, and log n, and an auxiliary space of big O and n. Next.
So for how it works, so first we need to define the merge sort function, which has three parameters, which is the array, the L as the first index, and the R as the last index. So if the R is bigger than L, we need to find the middle point to divide the array into two halves, which can be defined in this function. So the function is equal to M equals to L plus R minus 1, since the array starts from 0. So that's why it's subtract by 1. So and then it will divide it by 2. And the second is we need to call the merge sort for the first half, and then we need to call the merge sort for the second half. And finally, after the array is sorted, you need to merge the two halves sorted within the step 2 and step 3. So this is the demonstration of the merge sort itself. So as I've explained it before, so the first step, you need to split the sublist into two until you reach a pair of values, and then you need to sort or swap the pair of values if needed. And then the last is you need to merge and sort the sublist and repeat the process till you merge to the full list.
Merge sort algorithm is one of divide and conquer algorithm category. The philosophy of divide and conquer algorithm actually comes from divide et impera, which in politics and sociology is technique to gain and maintain power by breaking up larger concentration of power into pieces that individually have less power than the one implementing the strategy. This technique was later adapted to a computer science algorithm which divides the input array into two halves, calls itself for the two halves, and then merges the two sorted halves.
So from the facts that have been stated by my friends before, now we can group the facts into two parts: the cognition and computation. So the cognition for the algorithm is the problem solving to sorting lists of numbers or elements by breaking big components into fractions of smaller, manageable pieces, resulting in a stable time complexity of big O n log n, but with the addition memory space of O n. And the computation of the algorithm is based on the division of the list and the comparison between elements to sort the list. Next. So our thoughts behind the algorithm is that merge sort is algorithm with a stable sum complexity of the best, worst, and average case of O and log n, which is better than insertion sort, selection sort, and bubble sort. It is important because for an input n, it will scale slower than the other algorithms, thus making it fits for any size of algorithm. So it has its own disadvantage. It has merge sort has to make a complete copies of entire subarray in each recursive call. Thus, merge sort needed extra memory of ON. Okay.
So basically that's the end of our presentation. So thank you very much for listening. And if you have any question or just any question, please feel free to ask us. So assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you very much for this group. It's also a nice presentation too. You mentioned about the sorting algorithms. So in what if you try to connect it to the real problem? What kind of problem that maybe will be addressed or will be solved by these algorithms? Maybe do you have any example? Okay. Hello, do you hear my voice?
I'm sorry, sir, but we didn't, we didn't explore about the application of the merge sort or just search, just the basic stuff and also the philosophy behind the
Yeah.
algorithm. So I'm very sorry if we cannot answer your question.
Okay, but that's cool thing. But you also has a present the philosophy or the logical baseline of the algorithm that you has present. Yeah, so that's cool thing. So actually the application is very wide, and then it can be applied to any many then I think you already know that. So for like in many some development of the application for some reason or some purpose. The first place that we always do is sorting. Yeah, do the sorting things. Yeah. So that's something that it's not like to solve the real the point of the problem, but it can contribute to solve the problems. Yeah. So that's also the good one. Thank you very much for the presentation. And we go to the next. I think we already have the team from Aditya, please.
Yes, sir. My friends will prepare the PowerPoint first.
Okay, please. Thank you.
All right. We didn't know that there are other groups that use merge sort algorithm as their main topic in the presentation, but I hope that's fine. So good morning. Sorry, good afternoon, everyone. Good afternoon, Pak Mardhani. Today we'd like to present about the merge search algorithm. Our team is consisting of next please. Consisted of me, Aditya Julian, and then Alicia, and then we got Alma Mahira, Keisha Arya, and the last one is Shauki Abdurrahman. So what are we going to talk about in this presentation? So the first thing we would want to talk about is the cognition and the computation itself, what our perspective on it, and then we want to talk about the sorting algorithm. Then specifically, we want to talk about the merge sort, and we want to compare, and the last one is we want to compare between the algorithm versus the cognition and the computation, as you mentioned in the last meeting. So the first thing that we want to talk about is the cognition and computation. What are those about? So this is purely based on our perspective. So firstly, we were going to talk about cognition. The key of the cognition itself is the mining process, solve mental processes. So cognition itself, from our perspective, based on the explanation taught in the class, we can say that cognition is the result of the mining or thinking/solving processes. Next, cognition can also be defined as the process when we try to solve some difficult problems. The processes may start from when we try to find the components or puzzle pieces that may contribute to solving the problems, then arrange those pieces into some variables and do some sequential processes to those variables in order to make something, in this case algorithm, that is capable of solving the problems. Then it is pretty common also to define cognition as mental processes, which includes all of the things that the human mind is capable of doing in its natural state, namely memory, emotion, perception, imagination, thinking, and reasoning are all the common mental processes. So next is going to be computation. This is going to be my friend's part.
Yeah, thank you, Adit. So I would like to explain about computation. The key itself is computational cognition. It's computable and the computational theory. So the main idea of computation is that cognition is computable. According to the computationalism, all cognitive capacities can be explained as a form of computing. And then the next is mental process can be the result of algorithmic procedures that can be affected by emotions or attitudes or individual histories. Computers that implement cognitive procedures exhibit mental processes. And the example is the Gojek app. We use Gojek app to order food. The application is made based on human cognition. Therefore, the human cognition is able to be computed. We can say it is computable if the task of study G is computable if the algorithm is formal for G. For the next part will be my friend Keisha. Thank you.
Thank you, Shauki. In this section, we're going to uh, know why we use sorting algorithm. Algorithms can be said as the core part of computer science. Computer science students are expected to know how algorithms usually work, though it may differ depending on the algorithms. One of the famous and basic algorithms that computer science students learn is sorting algorithms. Based on gigs for gigs, a sorting algorithm is used to rearrange a given array or list elements according to a comparison operator on the elements. We choose this algorithm due to its simplicity in solving problem by comparison. Next. In this part, it will be explained by my friend.
Okay, thank you, Keisha. Hello, everyone. I will explain what is merge sort, which is an algorithm that we choose for this presentation. So merge sort is a divide and conquer algorithm. It divides the input array into two halves and calls itself for the two halves and then merge the two already sorted halves. Next, this is the visualization of merge sort. As we can see, it combines two array and then sort it and then combine it again and recursively just do that until everything is sorted. Next. So this is the real life application, an example of real life application of merge sort, which is for e-commerce. There's a section that is called you might like. You may often see it in your e-commerce applications such as Shopee, Tokopedia, and others. And this is an example of merge sort since the things that is presented in the you might like section is based on the things that you are interested about and often buy. So it is the things that is in the you might like section is presented because when it's sorted, it is on the top of your interest list. So this section will be about algo versus cognition versus computation and will be explained by my friend.
Thank you, Alma. So in this part, that's right, I'm going to explain about the cognition and computation of the merge sort. Okay. So as you can see, if you have ever watched tennis on TV, then you can understand the merge sort algorithm in JavaScript. To solve this cognition, we'll be using a tennis player as a metaphor. Okay. In this guide, we'll talk about how to understand the merge sort algorithm, which is the computation, and get around the cognitive traps that make it so difficult to understand. As our team concluded, Common problems in all coding languages around learning algorithms are how the number of lines of code does not match up with the complexity of the code, and also does not reflect the amount of mental simulation people need to do in order to understand the code. Okay, so as previously explained, in merge sort, you can only sort an array by comparing two elements at a time and finding the larger elements. Therefore, I'll begin from, wait, um, I'm sorry for an error there. Okay, I'll begin from the cognition. So the goal of cognition computing is to simulate human thought process in a computerized model, and in our cases is the tennis player metaphor. Okay. Okay. This is why we choose a tennis competition to solve the cognition, because the human mind is able to understand through the eye and logic to see which player is the best due to the result of human emotions, attitude, and even their individual histories. That's explained by my teammates before. Okay, so here, let's imagine that we have an array of 8 numbers that we need to sort from smallest to largest. Rather than thinking of this as numbers, let's think of them as skill levels of tennis players on a scale of 1 to 10. It's our job to determine who is the best tennis player of the group. So, to continue to the computation, in this case, we'll be trying to find the best amateur player in the United States. We can group these players into 4 regions: West, Mountain, Central, and East. It would look like exactly like this. Okay, so I'm going to continue to computation. As it is explained before, this part will determine the computational process from the previous metaphor. Okay, here is the algorithm. In order for the algorithm to work properly, it must be able to handle all arrays with at least 2 elements for merge sort. We will start with 2 regional tournaments and then run competitions between other regional winners to determine the national champion, like from the pictures, as you can see. So the function should take 2 arrays and combine them into one properly sorted array from the smallest to largest. And from the code, from the right picture, line 3 is when we start iterating through the players on both sides of the bracket. The number of iteration is determined by the longer array. Line 4 to 10, we compete with the first element in each array. And for the last one, we return the rankings array with the players ranked from worst to best. So in here, this part of the code, we will use recursion within the merge sort to repeatedly split up the array, like Alma said before, about how it is repetitively until you'll get 1 until 10. So in this picture, from the left, we can see how the array is splitting and then resembled from the picture beside it. And this is a great hint in why we will need recursion to solve the problem. So in this picture, this is the computation to solve the cognitive and the recursive part of the merge sort. As you can see, from line 3 to 5, allow us to define a midpoint in the array and split the array down to the midpoint. When we need this recursively, we shrink the array until it is a single element. The most important code is line 2 and 6. Line 2, we handle the case where the array has been shrunken to one element. This tells us that the recursion should stop and we can run the lowest level. And in this case is the regional tournament. And for the line 6, we define that in each call, we will run the tournament round bracket function on the sorted array from the previous call. And in this case, it's the one-on-one matchup. So in conclusion, cognitive traps can be easily solved if you have a clear explanation of the computation mixed with a metaphor, such as matching a tennis player competition from the best to worst based on two-player comparison. So that is all from our team. Thank you for listening. And sorry, and have a good day.
Okay, thank you very much for the team that present very clear and very detailed explanation. Yeah, thank you very much. It's also give us and the philosophy behind the algorithm and then how it's work for some tournaments. Yeah, so that's cool things. Yeah, so because I think when we see this this discussion, actually we have at least two kind of insight. And the first is the algorithm itself, like we discussed last week, and today is it can be some of the approach to solve the problems. Yeah, it's not only just the execution and the tasks and the following the order and so on, but the most important thing is how we solve the problem into efficient and effective way. And the second is about the application itself. So I think the algorithm can trigger us to have a lot of and a wide range of idea to do with the applications. Yeah. So the algorithm is will be the heart of the innovation actually. Not only just innovation, to solve the problem that occurs in the world. Yeah. So I think today we learn about it, and then hopefully we can have a deep knowledge on it, and we can still remember until in the futures. Yeah, especially for you, for your career, for your futures. So if you should still keep this one. I think there is no difficult algorithm to learn and to implement into your application or into your system. So basically the algorithm is only the logical thinking to solve the problems. Yeah. Okay. So I think we already have not a very free time now. Yeah. So we only have as of the rest time. So I think for today we will conclude until this point. And before I close, I will share to you the QR if you not scan your QR. Yeah. So and then I think I will close this session. I will we will not have any assignment for the next week. Next week we will meet again, and then we will discuss with the new materials, the next section to discuss. Yeah. So thank you very much for today, and stay healthy, and then good luck for your next courses, and thank you very much, and see you next week. Yeah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam warahmatullahi
Waalaikumsalam.
wabarakatuh.
Thank you, sir.
Yeah, thank you very much.